A very good morning to our madam. And in this morning, we're going to present our lab 4 determination of gravitational acceleration. So going to the objective of this lab is that we're going to investigate the simple harmonic motion SHM and its relation to the gravitational acceleration. So on the very first part of this experiment will be the part A, right? So we're going to do the mass spring system, right? Then we going to go to the website itself, which is this one, right? And first thing first is that okay, we going to set up everything first. So first displacements and natural length, we're going to take that. Damping, obviously we're going to put to none, and the gravity just let it be. Other than that, that's all. Then first thing is that okay, we're going to measure the original spring length first, right? When the spring is not moving, which is equilibrium state, right? Then we're going to take this ruler, then we're going to measure from the very top to the very bottom. Then it will be 48. Then we're going to input on the table right here for x0 millimeter. Then after that, we're going to do the very first one. Basically, in this table is that we need to find the elongation of the spring. Then the first one will be 50 gram, right? Then we need to put the mass to 50. After that, this is the load that we will get. Then we just put this load onto the spring, right? Then when it's bouncing, we just click this button stop. Then after that, we're just going to take the final position minus the initial position, then we will get the elongation of this spring, right? Then this one will be okay, obviously you can see it's 56, then 56 minus 48, then we will get 8 xcm, then change the millimeter will be 80, then do the same thing for the rest to the 300 gram. Then that's how we get all this value. Do first try, second try, third time, then after that we get the average. Then for the time taken, right, we're going to go back here, right? Then we're going to use this stopwatch, and we're going to pull this spring to one position. Let's say if we pull to here, then we're going to release it, and then you'll see it keep bouncing, right? Something like that. If you pull it on the middle, then obviously the other mass you also need to pull from the same position. So I'm going to take the very end as my position. So what we're going to do is that we pull this down, then we release it. So once we release it, we're going to at the same time open this stopwatch. Not open, I mean start this stopwatch. Then when we pull down, release it, and when it bounce back, then we count that as one wave, right? So we're going to wait until it done the 25 wave, then we're going to stop the stopwatch, then we will get the value that we input on the table. So giving a quick demonstration will be something like this. Drag all the way down. The moment we release, we click the stopwatch, which is like this. Right, so basically wait until 25 times, 25 wave, then eventually we will stop the stopwatch, then we get the value and input to the table. After that, do first try, second try, third time, and then after that get the average. So after we input this 4 column here, then we're going to do the periodic time. Then the formula for this would be you use the time taken, right, divided by the number of oscillations, which is 25, then you will get the value. After that, this T2 will be the square of this value, and that's all for this table for the part A.
Okay, next for part B experiment, which is pendulum system, we can see the procedure. So firstly, we need to go to the link and click the play mark and choose the lab section. Then set a mass to 0.50 kg, take a stopwatch and set friction to none. Then set the length of string according to table 2. Click on the mass and bring it up until 50 degree and release. And by using the stopwatch, measure the time taken for a predetermined number of swings, which is in this experiment is 25 swings. And then increase the length of string, repeat step 4 and 5 for 6 readings, and record the data in table 2. Okay, we go to table 2. As you can see, we need to find the time taken, calculate the periodic time T, and calculate the T square. So as we want to run the simulation, I will take one example of the value of length of strength L, which is I will take the value 0.40. Then we go to the simulation. Then firstly, I will set the mass to 0.50 kg, and then friction to none. Set the length to 0.50 meter, as we choose just now, and then we will click the stopwatch. Yes. And then we click the mass and drag it until 50 degree, and then we release it. And the way we want to know how the one complete swing is when the mass is released and it swing back and forth until 50 degree, which is its original place. And then it is called as one swing. Then we will release the mass and start the stopwatch. Then we will count until 25 swing, and the time taken for complete 25 swing is taken. Okay, after we get the 3 reading of the time taken, we can calculate the average of the time taken. Then after that, we can calculate the predict time T, and the formula is predict time T is equal to time taken average over number of swing. So the average that we had taken is divided by number of swing, which is 25. So we get the answer, and then we can calculate the T square and just square it of the, and we just square the T. Okay, next is question and discussion. By using Excel, plot a graph of T square versus elongation of spring for part A and T square versus length of string for part B. From the both graph, determine the slope of the graph. So for the part A, the graph is T square versus elongation of spring. Okay, as we can see, the y-axis is T square and the x-axis is elongation of spring. So the equation, so we plot the data that we have taken in the table, and then we plot it. Then the equation that we get from the graph is y is equal to 0.0041x minus 0.021. Then from and then for the part B is T square versus length of string L, and for the y-axis is T square, and for the x-axis is length of string. Then we plot the data that we have taken in table, then we get the graph, and the equation is y is equal to 4.4403x minus 0.0058. Then for the slope, how we calculate the slope is m. Then we can so for part A, we can see the equation y is equal to 0.0041x minus 0.021. So as we know, the equation of the graph is y is equal to mx plus c. Then m is, in this equation, m is 0.0041. And same goes to the part B. Slope part B is 4.4403.
So moving on to question 2, we're going to determine the value of gravitational acceleration for both situations, right? So giving the formula that we get will be, okay, gravitational acceleration equal to 4 pi square the length divided by the t square. Then part A we will get 9.57 millisecond, part B we will get 8.77 millisecond. Going to the question 3, compare the value gravitational acceleration g from part A and part B with the theoretical value of g, which is we know that the theoretical value will be 9.81 millisecond. and then we're going to find the percentage of the difference, right? So we know that the percentage of difference will be theoretical value minus the experiment value, which is from the part A and the part B, divided by the theoretical value, which is 9.81 again, multiplied by 100%, then we will get the percentage of the difference. So on part A, then we will take theoretical value 9.81 minus the experiment value of part A, 9.57, divided by the theoretical value 9.81, multiplied by 100%, then we get 2.44%. Same goes as part B. So going to the question 4 from this experiment, what the main factor that determine the gravitational acceleration? So we know that in this experiment, the main factor in determine gravitational acceleration are the mass and the length of the string. According to the Newton law of gravity, the factor that affect gravity are mass and separating distance. For mass, an increase will be caused as increase, cause an increase in gravitational force. The increase in separating distance caused the reduction of the gravitational between two bodies.
Okay, for the conclusion, at the end of this lab session, we will be able to recognize the importance of simple harmonic motion and its relation to acceleration. For instance, velocity and acceleration in simple harmonic motion. A motion is said to be accelerated when its velocity keeps changing. But in simple harmonic motion, the particle performs the same motion again and again over a period of time. In the experiment part A and part B, we acknowledge that the main factors in determining the gravitational acceleration are the mass and the length of the string, in which an increase of mass would cause an increase in gravitational force, while the increase in separating distance causes the reduction of the gravitation between two bodies. Okay, thank you. Love you.
Love you too, madam.